Good morning and welcome to this session. Basically, this is the last live session we're going to have together. We have an exam this Thursday. That's exam 3. And then we have the final next, Thursday from this Thursday. So it's going to be the 12th is going to be exam 3. The 19th is going to be the final, okay? I know that you guys did the post exam, and I think there was a problem with one of the questions. Okay, for some reason, I think I made a mistake in the actual question itself. So I'm going to go back and revisit it to make sure that it was wrong, because most of you got it wrong. And I think because the question itself is wrong. Okay, it has to do with the energy levels for n equals to 7 or something like that. And the answer should be 98, because 2 times 7 squared should be 98. But for some reason, I didn't see 98 as one of the choices in there. And some of you were guessing left and right, of course. You don't have the correct answer. So I'm going to override that to fix that. And then that's one thing. The other thing also, we were talking before we started the recording about the final. The final is going to really pull from the actual exams that you have. The number of questions is more. I'm not exactly 100% sure, but I think it's about 8 questions in it, okay? So usually it's more, but again, because you have done all of the exams, you have done all of the others, so it's really comprehensive, and it goes from exam 1 all the way to exam 3, covers all the topics basically that you have done up to that point. So this is in terms of the final. In terms of the exam 3 focuses on only chapters 41, 42, 43, and 44. After I looked at those problems, as I was saying, it seems like you have quite a few of them to basically ready you for the exam. And since I gave you last week what these things are, so I'm hoping that most of you, and I know some of you are not here right now, about half the class is not here, is not live at least, that you have had a chance to go through all of them. And I'm going to pick a few of them and discuss them. I'm going to discuss all of them in general, the ideas behind them, so that we have a feel for what they do. And then you go through them and work all the details and everything else, okay? Some of them are tedious, long, and some of them are not. So without further ado, unless you guys have a question, we can dive right into chapter 41 problems. No? Okay, so in that problem, I gave you problem 30 to start with. And problem 30 gives you germanium. So those two problems, 30 and 31, actually are kind of, I think, straightforward. All you have to do is have access to a periodic table of some sort and look at the case of for problem 32, which is germanium. And germanium in here tells you that Z is equal to 32. Actually, you really don't need the periodic table, but you need to know how the energy levels are arranged, okay, in terms of their values. Some periodic tables, like the one I have in here, gives you the different energy levels. So you have the 1s state, which is basically the lowest energy level. Then you have the 2s, the 2p, and then the 3s, and the 3p, and the 4s, and then the 3d, and then the other one, the 4s. So if you follow this, you're going to find the Z equal to 32. So you start adding the numbers in here. Some of you did this stuff in chemistry, so you're very familiar with these things, okay? If you did not, then this is actually not hard to understand. And this is true for problem 31 and 32, okay? So these are easy, aren't they? Yes?
Yes.
Okay, very good. So problem 44. Problem 44 gives you basically a 3D harmonic oscillator. One of the properties of this harmonic oscillator in this problem is that it is a symmetrical harmonic oscillator. I mean, isotropic harmonic oscillator, meaning the spring constant is the same in the x direction and the y direction and the z direction. So there is symmetry in here. So we expect degeneracy. Whenever there is symmetry, we expect that the wave functions basically will be degenerate for the same value of the energy. So the energy levels will be degenerate in a sense. So, and then they tell you to use, because now we have a 3D problem, not a 2D problem, not a 1D problem, to use basically the solution as just being the product of the different components in the X direction, the Y direction, and the Z direction. And of course, different quantum numbers, they don't have to be necessarily the same, nx, ny, and z. And you're supposed to put them in Schrodinger's equation. And since the potential has the x value squared by itself and the y squared by itself and the z squared by itself, what you can do in this case is just divide by the wave function and plug in the values that you have for them. Each and every one of them, they tell you that satisfies its own basically harmonic oscillator for 1D. So you divide by that, and at the end, you will find the energy level is simply equal to the sum of the different energy levels. So it's going to be Enx that is given to you, which is nx plus 1/2 h bar omega, plus nx, ny plus 1/2 h bar omega, plus nz 1/2 h bar omega. Take the h bar omega as a common factor, and you will find that the energy level in this case is going to be nx plus ny plus nz plus 3 times 1/2 or 3/2 of h bar omega. So the ground state in this case is going to be nx equal to ny is equal to nz equal to 0. And the ground state is going to be exactly 3/2 of an h bar omega. So that is something that is different from the one-dimensional, because the one-dimensional was only 1/2 of h bar omega. But then when the next energy level is going to be degenerate, namely one of them is 1, the other two are 0, which one is 1, which one is the other two, then that is a degeneracy. In this case, can be nx is 1, the other two are 0, or ny is 1, the other two are 0, or nz is 1, the other two are 0. The energy in this case is going to be absolutely the same value, which is 5/2 basically of h bar omega. But it has 3 different quantum states. So that's basically what the problem is. So this is not hard to proceed with. Sounds good?
Yep, sounds good.
Okay. So the next problems are problems 51, 52, and 53. 51, 52, and 53. Okay, 51 is kind of a little bit, involves a little bit of calculus, because this is a what it gives you in this case, they give you already the 2p state, okay? So they give you the 2p state, and they give you the radial expression of the 2p state. Remember, for the hydrogen atom, it has 3 basically, or 2 at least. You have the radial function that depends on r, and you have the one that depends on theta and phi, and that involves some complicated basically Legendre functions. But the point being in here, forget about those. You're given r, the dependency on r in this case. But then they also tell you the probability distribution in this case is PR. dr, the actual probability, not the probability distribution, where in this case it should really be the wave function squared, psi squared, times the element of volume. And the element of volume in the case of the sphere is going to involve r squared dr. It's going to involve plus the sine theta d theta d phi. You integrate over d theta d phi, and at the end, all you're left with is the r squared dr. So they gave you the expression. So they give you the expression as being just being r squared, the big r squared, times a little r squared dr. So all you have to do is just combine everything, and now you have an expression for the probability density, which is p sub r. And at this point, they want to know at what value of r is p sub r for the state of it is maximum. So all you have to do is take its derivative. Take its derivative and equate it to 0. You find where the maximum of that function. Obviously, for r equal to 0, this function goes to 0 because you have an r squared in there, and you have another r in front of the exponential. So when you square that, it's going to be r to the power 4. So for r equal to 0, that goes to 0. Probability density has to be always positive or 0 at least. And then for r equals to infinity, the exponential also kills that function. So it's 0 at both ends. and somehow it has a maximum, and that's what you're supposed to find. And then compare that to the Bohr's model. Remember, in the Bohr's model, the radius was equal to n squared times a naught, where a naught was supposed to be Bohr's radius. In this case, Bohr's radius is actually equal to a. They just gave it the value of a instead of a naught. So at the end, you should be able to find the same answer. Okay, you should be able to find the same stuff. You should, when you do the maximum of that function, you should find that both models, whether the Niels-Bohr's model or the actual Schrodinger's equation, when you solve it, gives you the correct location. But that's a maximum. Remember, in the case of Schrodinger's equation, it's distribution. If you actually try to locate an electron at that state, it may not be in that location because it's kind of spread around, okay, that location. But it's maximized in the where the Niels-Bohr model predicts its position. For the Niels-Bohr problem, it's actually a fixed location. It doesn't change, it doesn't spread in space. But this one, it could be as low as basically around the nucleus and as far as infinity, albeit in both cases with zero probability, okay, or small probability. So that is 51. And then 52. 52, it says the interstellar hydrogen emits characteristic microwave radiation that can be understood as follows. Model the magnetic moment of a proton, mu p is equal to E over 2 mp. Remember, that's what we found for the electron when we did that model, except that we used the mass of the electron, not the mass of the proton, times the spin in that case for the electron. This case is going to be the spin of the proton, okay, which is the same value. Both of them are fermions. They happen to have half integer spins, okay, except that the mass in this case is going to be the mass of the proton. So this magnetic moment will be a lot smaller in magnitude by almost 2,000 factors than that of the electron. They give you the mass of the proton, and they give you a z. It has two possible values, plus or minus h bar over 2. Model the proton as a current loop with a radius rp equal to 0.85 femtometer, just slightly less than a femtometer, which is the size of a typical proton. So now what they want to know, what would this current produce in terms of magnetic field? For that, you have a current on a basically going in a loop, okay? That's what the electron we're trying to argue in this case is. So you have a current going on a loop of radius 0.85 femtometer, okay, which is a ridiculous small size, okay? And so they want to know the value of the current, I, okay? So you have a mu. Remember, mu from physics 2 is equal to the current times the area. And the area in this case is going to be pi r squared. So it's going to be that radius that was given to you squared times the current should give you that same mu, that same magnetic moment. You have mu, you can calculate it. You have MP, you have all of the terms in that expression. You have E, you have S in this case, which is 1/2 of h bar. So you have all of the values that you need for mu. But then you equate that value to pi times r squared times the current. From here, you don't know what the current is. You can calculate it. Okay, it should be a huge current. But that's basically how proton is so tiny, spinning so fast in this case, producing that magnetic moment that you calculate. Albeit it's a small value, but it's still going to be a big value for the current. So you find the current. And then B, the magnetic field at the distance x from along the x axis of the current loop is given by equation 2815. That too is way back from physics 2. Basically, when you have current in a loop, is going to produce a magnetic field at a distance x from it. You use Biot-Savart law, where you have, in this case, you take an element from that current and you find the magnetic field using that law. You cancel all of the components. The only component that is going to be to stay is going to be along the axis of symmetry, because the components in the y direction or the z direction or whatever other direction, the two directions basically will cancel out if you're taking this to be the x direction. So in that case, that value is going to be when you take the integration, when you sum throughout all of the elements of the current, that distance doesn't change. You're going through a loop, so that distance doesn't change. The distance x is given, the distance is given. Otherwise, forget about what I'm talking about. Just go to equation 28.15. That tell you to do that. So if you go back into chapter 28, you will find the expression from chapter 28. Use that expression. You don't have to prove it. Actually, it's in page 942 as a summary of the equations. Okay, so it gives you the magnetic field. It gives you the magnetic field as a function of the current times the radius squared. And the radius is that 0.85 femtometer squared divided by 2 times x squared, where x squared is the distance, how far you are from the loop, how far you are from the proton in this case, plus a squared, where a squared, again, radius in this case is just 0.85 femtometer. So that is basically the expression, but use the distance as being that of the half, basically the nearest Bohr's radius, But Bohr's radius is of the order of an angstrom, or half an angstrom. It's still a very, very, very big value compared to a femtometer. So you're going to neglect the femtometer. You're going to neglect in the denominator the A term in there, the radius of the proton, because the radius of the proton is the order 10 to the negative 15, whereas the electron is a distance of 10 to the negative 10, which is 100,000 times further away. So you're going to be neglecting it in the calculations. So it's going to be fine. And the potential energy in this case is going to be, so now you are in the position of the electron, feeling the effects of the magnetic field created by the proton. So now you have mu of the electron times B. This is the potential energy in this case. You're going to find the two values and the fluctuations in it. Does this problem make sense to you guys?
Yeah, it does.
Okay, very good. So you're just building a model based on stuff you learned from physics 1, physics 2. I mean physics 1, physics 2, and physics 3. Okay, sorry. Although physics 1 is also involved. Okay, to find that dynamics in there. Anyway, the next one is 53. 53 is the hydrogen spectrum includes 4 visible lines. Of these, the blue line corresponds to a transition from n equals to 5 to n equals to 2. Okay, shell and has a wavelength of 434 nanometers. So the lambda is given to be 434 nanometer. If we look closer to this line, is broadened by the fine structure due to spin orbit coupling and relativistic effect. So you're going to be using equation, the one that we have from this problem in here. So let me go to the summary, we should have it. It's 4141, okay? 4141 gives you the different energy levels at N and J, where J is the basically the coupling between the spin of the electron and what it is in orbit, basically L, okay? So that gives you, J is actually the sum of both, in this case, L plus S, okay? So that's the two values in there. Plus, what I mean by plus, it's a vector plus, okay? So you're going to find the absolute value in this case, that's going to be the, or the magnitude as being just L plus or minus, in this case, 1/2, okay? So that's basically how you find J. And how many different sets of L and J quantum numbers are there for n equals to 5? For n equals to 5, you have 5 values for L, 0, 1, 2, 3, and 4. Okay, for each and every one of them, you have different values for J, yes. For 0, that's going to be 0 plus or minus 1/2 in absolute value, so it's going to be 1/2. For 1, you're going to have 1 plus or minus 1/2. Plus 1/2, that's going to be 3/2, so there is a value for 3/2, and there is also 1 minus 1/2, which give me 1/2. So there is two possibilities in here. And there is also another one, which is for L equals to 2. L equals to 2, you will have again 2 plus 1/2, that's 5/2, or 2 minus 1/2, that's again 3/2. So you have 3/2 from both sides, and you have 1/2 from this 2. And then you will also have 5/2 from here, and you will also have 7/2 and a 9/2. So basically, because you are at the end, you're going to have 4 plus 1/2, which is 9/2. So those are all the possibilities of J in this case. For each and every one of the values of L, you will have 2 values for J. That is for n equals to 5. For n equals to 2, it's easy because then you will only have 2 L's. You have L equals to 0 and L equals to 1. For L equals to 0, again, there is only one possible value, which is 0 plus or minus 1/2 in absolute value. So it's going to be 1/2 for J. For L equals to 2, then you also have 1/2, which results from 1 minus 1/2 in absolute value. So it's another 1/2. And for also L equals to L plus 1/2, that's 3/2. So you have basically the two possible values are actually in this case 3/2 and 1/2. Okay, because look, this problem in here at some point is going to ask you for En of J. The energy E does not depend on L. It depends on L indirectly, if you wish. It depends on actually on J explicitly, if you look at the equation 41. So all of those repetitions for the values do not matter, because for n equals to 5, n is 5, fixed. Now J has, it looks like you have several possibilities. You have what, 9 possibilities or something, but it's not true. You have a lot less, because you could have 1/2, you could have 3/2, you could have 5/2, you could have 7/2, and you can have 9/2. Those are the only 2 possibilities for J in the case of 5. In the case of n equals to 2, you only have 2 possibilities. J could be 1/2 or J could be 3/2. End of the story. Okay, but then don't forget what's the word now? The transition rule in this case, that the momentum needs to be changing. You need to impart some momentum with either a left or a right, basically polarized photon. So in this case, L can change by plus 1/2 or minus 1/2. So L plays a role in this case. It has a transition in this case to see which ones are allowed. Okay. Then you're going to find the maximum and the minimum, and that gives you how much the actual 434 nanometer is broadened by this effect. Okay, so if you look at it with a finer, basically diffraction grading, you're going to see it not exactly sitting on a single line, but it's slightly broadened. Make sense, this problem?
Yeah, it makes sense.
Okay, very good. It's long and tedious, but if you don't lose sight of the rules, you should be good. If you start doubting yourself and probably not sure exactly what's going on, then you might encounter some difficulties, because as I was saying, this calculation sometimes can be your calculation corrections. I mean, 434 is 434, but you're going to change it slightly at the end, add this little bit to it and subtract a little bit to it, and you find how broadened it's going to be. It's going to be a small addition to it. Okay, so it's going to be long, but hopefully you guys will not have problems with it. Okay, so if one of you, please do not feel intimidated, ask the questions, but if some of you want to have this discussion later on, I'll be more than happy to discuss it, and send me a message and we can sit down and basically work out whatever issues that we can fix to make sure that you don't have problems with these things. Okay, 53, then we have 58. 58 is, as a matter of fact, similar to, let me read it first. An electron in a hydrogen atom is in the 2p state. In a simple model of the atom, assume that the electron circles the proton in an orbit with radius r equal to the Bohr's model. So in this case, for n equals to 2. So it's going to be 4a0. The book sometimes uses the standard convention for the Bohr's radius, but sometimes it doesn't. The standard notation for it, it's a0. Basically, that's the Bohr radius. Assume that the speed v of the orbiting electron can be calculated by setting L, the angular momentum, equals to mvr. So that's from physics 1. And taking L to have the magnitude given by the value for the 2p state. Remember, the 2p state is L equals to 1. I mean, the little l, not big L. The quantum number L is equal to 1. So if L is equal to 1, then the value should be just square root of 1 times 1 plus 1 times h bar. That's how much angular momentum from here. So from here, we have R, they gave us R, which is basically just give it from Niels Bohr's model, which is m squared. In this case, it's going to be 4 times a naught. And then we have the mass of the electron. So we have two components in that angular momentum. We have the mass of the electron, we have R. We don't know what the velocity is. But then we have what the big L is, which is just the square root of 1 times 1 plus 1 times the whole thing after you take the square root times h bar. Okay? So we can find what that velocity is, basically. That's my point. Okay? Model the orbiting proton as a circular current. Wait a minute. Where am I? Okay, sorry. In the frame of the electron, the proton orbits orbits with radius r and speed v. So basically, we flip the picture as if you are sitting on an electron and you see, in this case, the proton zooming around you. Okay, it's like we are now on Earth. Basically, we look at the sun and the sun comes in and out all the time, so it's moving around us. But you and I know that the Earth is actually the one spinning around the sun, not the other way around. So this is the same picture. Imagine that you are sitting on the planet electron and you're looking at the sun, proton in this case, going around. So that's basically the picture that you have in this picture. In the frame of the electron, the proton, model the orbiting proton as a circular current and calculate the magnetic field it produces at the location of the electron. Again, this is similar to the previous problem we were talking about in this case, except in this case, you're going to do it for this hydrogen, for this level, for this specific energy level, unless the first value that's given to you for R. So this is different value. So you're going to find a different value. So now you have the charge of the proton. You have how far it is from you in this case, and you have how fast it's moving. So you can calculate the current as simply being equal to the charge per unit time it goes around you. And you know how much unit time you have. The period is equal to the whole circle, in this case 2 pi r, circumference, divided by the velocity. And the velocity, you computed it from the first step. So now you have the time. All you have to do is take the charge divided by the time, and now you have the current. You have the current, again, you go back to chapter 28, and you find using Ampere's law, if you wish, or use Bjorn-Savart's law in this case, it doesn't matter which one, and you find the value of the current. As a matter of fact, let me go back into chapter 28, give you a formula that might be able to help you do that. It's basically 2817, except the number of loops in this case is equal to 1. Remember, it gives you the number of turns, mu naught times I. You just computed I, which is the charge divided by time, by the unit time in this case. And mu naught, which is what? 4 pi times 10 to the negative 7, divided by 2a, and a is the distance in the radius of the loop in this case. Times n, number of turns, you don't have many, you have only one proton orbiting the electron in this case. So this is easy, isn't it? Yes? Are you guys awake?
Yes, sounds good.
Okay, so what are 59 is kind of a silly problem, but I thought it's fun to have. Doesn't mean that it's not, might not be a question in the exam. In a weird universe, in another universe, the electron spin is 3/2. So rather than spin 1/2, but all other properties are the same in our universe. In this universe, what are the atomic numbers? It's not really silly. You have to be careful, okay? One of the things that is kind of unique to our universe is those constants. So one of the theories in physics is that universes are created all the time, but because their constants are not yielding, they most of the time decay quickly or basically evaporate quickly. So our universe happened to have the right number so that it's stable. So this is a potential universe. Let's put it this way. But all the physical are so in this universe, what are the atomic numbers of the lightest two inert gases? So in this case, inert gas, that means that all the energy levels are filled. So the first one has to have, in this case, look, you have spin can be 3/2. That means you can have positive 3/2, positive 1/2, negative 1/2, and negative 3/2. So you have to have 4 electrons in the ground state. If they are there for n equals to 1, basically in this case, L equals to 0. So in this case, you don't have anything else. You don't have ML, you don't have ML is equal to 0. So it's a symmetrical state. So in that case, you have to have 4 electrons to fit it. So that's going to be beryllium. So the first, so beryllium will be inert, basically. That's basically what that means, because it has four electrons in the outer shell. And the second one is, what are the atomic number of the lightest 2? And the next one is going to be for n equals to 2. Again, you're going to do the math in this case, because again, for the 2s, you guys need 4, and for the 2p, it will need, because p is L equals to 1, L equals to 1. I'm sorry, yeah, L equals to 1. So, wait a minute. Yeah, ML can be in this case -1 or 0 or 1, and in every one of them, you can put 4 electrons. So in this case, you will have so many numbers in there. So it's going to be around 20 or something like that. Okay, so all you have to do is just go through these numbers, quantum numbers, namely n equals to 1 and n equals to 2. For n equals to 1, it's easy because L is equal to 0 and m is equal to 0. So in this case, you only have 4 electrons. For the case of n equals to 2, then in this case, L equals to 0, then again, you have 4. But for L equals to, and 4 plus previous 4, that's already 8, okay? Plus another L equals to 1, then in this case, ML is going to be -1 or 0 or 1. And each and every one of them, you're going to put 4 electrons. So you'll have 4 times 4 times. So that's 12 plus 8, that's 20. Okay, so Z is equal to 20. Okay, so I think this problem did it in detail. Okay, and then the next one is 60. So lithium atom has 3 electrons in the ground state. And the configuration, they give you a configuration and the 1s state. And a photon with wavelength 67 point something is emitted from the transition of 3/2 to 1/2. So that's due to the split orbit coupling. And a photon of wavelength 67.000, whatever, that's also different. Transition, calculate the effective magnetic field seen by the electron in the state of the lithium. Okay. So you have, yeah, you're splitting the wave, splitting the level there to the spin orbit coupling. If you have these 2 values of lambda, you're going to find delta E from it using basically the expression, which is hc over lambda. Take the derivative if you wish and divide it by the product of the 2 waves. And there is an example actually from the book you need to follow. And they tell you example 41.7. Just go back into the example 41.7 and follow the similar steps in here. And now you're going to find B, because remember this splitting is due to a magnetic field. So it's a mu times B. So you're going to find that is how much that energy difference is going to be. So delta E in this case is you're going to equate it to the mu for the electron, which is the value, which is the Bohr magneton times the 2 with the better value 2.033 or some 2.00323. And then at that point, you can find where the magnetic field is, okay? If in doubt, just go back to the example. And again, if you have difficulty, please let me know. We can go through that example in detail, okay? But I think I need to pick up the speed actually a little bit. Okay, so that's 63 is data, and data, all you have to do is represent it and answer the questions that are related to it, okay? Doesn't mean data are not out there, so data are potential questions. So we spent about half an hour on this chapter. Let's gain a little bit of speed on the next chapter, which is 42. Granted, some of them are actually lighter than others in terms of numbers. I mean, the last one has only what, about 6 problems or something, okay? So 32. 30 says when a diatomic molecule undergoes a transition from the L equals to 2 to the L equals to 1 rotational state, a photon with a wavelength 54.3 micrometer is emitted. What is the moment of inertia of the molecule for an axis through a center of mass and perpendicular to the line connecting the nuclei? Okay. So we have a diatomic molecule. So in this case, the energy levels goes from, okay, so in this case, the energy is given by the expression that we have, which is what? Square root of L times L plus 1 times H bar times omega. So it's going to be basically the values that we have in there for the energy for different values of L. L is equal to 1 and L is equal to 2. And we're given the wavelength. And when we're given the wavelength, in this case, since we're given the wavelength, we have delta E already. Delta E is hc over lambda. H is a constant, C is constant divided by lambda. Lambda is a wavelength that was given to us. So we can find what that energy is. That is one way, okay? Oh, I'm sorry, did I say, yeah. Let me look into the expression in here for the rotational energy from this chapter in here. H bar squared over 2I. L times L plus 1 times H bar squared over 2I. So that is the energy of rotation. I'm looking at equation 42.3, okay? This is the argument we made there. All we did basically is that we argued based on classical mechanics, physics 1, physics 1, that the kinetic energy of rotation is the angular momentum L squared divided by 2I, similar to P squared over 2I for the linear momentum. The angular momentum squared over 2I, where I is the moment of inertia. But in this case, the angular momentum is quantized, is equal to, by itself, square root of L times L plus 1 times H bar. You square that, now you have the angular momentum, which is L times L plus 1 times H bar squared. Divide that by 2I. Now you have an expression to find what I is. Each bar is given. You know what that is, 1.055, 1.00545 or something, 10 to the negative 34. The 2 is given. I'm sorry. And then the L, you're going from different values of L, from L equals to 2 to L equals to 1. So you can find the difference between them. And for L equals to 2, you will have 2 times 2 plus 1, which is 3. That's 6. But don't forget you have 2 in the denominator. 6 over 2 is going to be 3. For L equals to 1, you will have 1 times 1 plus 1, which is 2. 1 times 2 divided by 2, so it's going to be 1. So one of them is going to be 3 times H bar squared over I, and the other one is going to be H bar squared over I. Take the difference between them, and it's going to be 2 times H bar squared over I. That you equate it to the value you compute from for the energy, which is equal to 54.44 micrometer, which is H times C. Cancel one of the H's if you like before you sum the numbers. I mean, there is an H bar and H on the other side, and they're related. And then you have C, the speed of light, divided by the wavelength lambda. Lambda is given. So in this equation, you have everything. The only thing you don't have is the moment of inertia. Calculate the moment of inertia. That's the question. Okay. Sounds easy.
Yeah, just to double check, the relationship between H bar and H is that H bar is H divided by 2 pi, right?
That's correct.
Okay. Just making sure.
When I was young, the only thing I memorized was H. So I always put this expression and calculate H bar. Okay. So you ask me what H bar is, I tell you it's 6.626 divided by 2 pi. Okay. Thank you, but I don't think so. I'm a grandpa now. I have 2 grandchildren. So okay, anyway. The next one. The next one is going to be, I'm looking at the problems in here. I have written them in my notes. Which one was it? 32. Oh, we didn't do much. Okay, 35. 35. Consider a gas of diatomic molecule moment of inertia I at an absolute temperature T. If Eg is a ground state, energy, and an Ex is an excited state. Okay. Okay. Then the Maxwell-Boltzmann distribution predicts that the ratio of the numbers of molecules in the 2 states is given. So we have this expression, we used it extensively. Actually, it's related to Gibbs free energy. And so that's in this case, you have the number of excited states over the ground states is given by that exponential of the difference between the 2 energies divided by kBt. Okay. Explain why the ratio of the number of molecules in the L rotational energy level to the ratio of the molecules in the ground state L equal to 0. So when you do the difference between them, L equals to 0. So Eg is 0 in this case. But Ex is given by that same expression that I was talking about in here, which is L times L plus 1 times H bar squared over 2I. Okay. Is given by this expression, and the only reason why you have that 2L plus 1 term is because of ML. For a given value of L, you have so many MLs that are involved, and you have actually 2L plus 1 of them. Remember, you have plus L, you have L minus 1, L minus 2, L minus 3, and so on and so forth, all the way to 0, and then you start with a negative value all the way to negative L. You have at some point negative L minus 1, negative L plus 1 when you do the when you remove the parentheses, and then at the end negative L. So you have 2L plus 1 of them. So that's why you have this many times that exponential. So for a given n excited state, you have a degeneracy in this case of the order of 2L plus 1 when it comes to this numbers in here. So that's where that factor is coming from. And then at the end, determine the ratios NL over NO and 0 for carbon dioxide. So in this case, we know what I is. We can find the reduced mass between carbon and the oxygen and multiply it by the interatomic distance between them. And I think that was one of the examples at 42.2. So you can find the value from there already for I. So the I, you can find it from that example. Once you find that I, then you plug it into the expression in this case, and they tell you to take the temperature to be 300 Kelvin. So T is 300 Kelvin at room temperature. So we're going to find the number, how many molecules are in excited state for carbon dioxide and how many molecules are not in excited state for carbon dioxide, monoxide, I'm sorry, carbon monoxide in each of the, every one of them. You will notice, if you do the calculations, that for L equals to 1 and L equals to 2, the numbers are going to be significant. As you move along, for L equals to big numbers, the number starts to drop down. Okay, And the reason why that is because you have the exponential of negative L squared, basically. That is going to kill everything. Yes, you have a term, leading term, that is linear in L. As L increases the numbers, the ratio increases. Initially, it does, because the exponential at that point is still kind of insignificant for low values, because exponential of 0 is 0. Exponential of 0 is 1. So it's not going to matter. But then for larger values of L, it takes over. Kills the leading term in that. So this should be straightforward calculation. And again, if you have difficulty with it, please let me know. Okay. The trick with this problem is has to do with that degeneracy. That's all. But after that, the substitution should not be a problem. And then understanding what's going on should not be a problem. That means that as the temperature, of course, increases, KBT increases, that allows for larger L's to be involved. So more and more excited states are going to be there. But as temperature decreases, as temperature goes down, only certain values of L will be involved. Otherwise, the molecule in this case will settle down to the lowest energy possible. Okay, so that's typical behavior of elements in this case. Okay, so that is 35. 38. 38 is a long verbiage in it, but at the end the calculation is kind of light. Okay. So basically it tells you our galaxy contains numerous molecular clouds, regions many light years in extent, in which the density is high enough and the temperature is low enough for atoms to form into molecules. Most of the molecules are hydrogen, basically gas, but a small fraction of the molecules are carbon monoxide, so CO, such as molecular clouds in the constellation Orion. So that's the picture in there, okay, was made with an ordinary visible telescope. The lower image was made by a radio telescope tuned to a wavelength emitted by carbon monoxide, okay, like the James Webb, basically using shorter wavelength. I mean, longer wavelength, I should say, okay. In a rotational transition, the different colors in the indicate regions of the cloud that are moving either toward the blue or toward the red relative to the motion of the cloud as a whole, as determined by the Doppler shift. Since a molecular cloud has about 10,000 hydrogen molecules for each carbon monoxide, it might seem more reasonable to, okay, so the verbiage in here is very long. Okay, using the data in example 42.2, calculate the energy wavelength of the photon emitted by carbon monoxide going from transition L equals to 1 to L equals to 0 rotation. So again, you're going to go back into that one. You have the energy for the rotation, L times L plus 1 times h bar squared divided by 2I. And you're going to find the transition from L equals to 1 to L equals to 0, okay? And you have I in that case, okay? So you're going to find the wavelength, we're going to find lambda, okay? And B, as a rule, molecular and gas temperature will be found in a certain excited rotational energy level provided by the energy from, as is shown in the previous problem 35, basically, that we just discussed. Okay, use this rule to explain why astronomers can detect radiation from, basically, once you find that, the value of lambda, you're going to change the temperature, calculate the temperature KBT using this expression in here, okay, from the previous example that corresponds to that excited state. And you should see values for KB, temperature around 20 Kelvin or something like that, okay? In other words, you're going to find the values that correspond to higher temperatures, okay? So even though the temperature is super low in those clouds, it's still high enough to excite those carbon monoxides, okay? As I was saying in the example from 35, as the temperature is lower, obviously you're not going to get to higher and higher excited state, but you still, even at 20 Kelvin, you should be able to get some of them excited enough to be detected by the detectors, okay? So these are kind of related to one another, 35 and 38, and the example from the book 42.2, okay? So we need to speed up these things. 41. 41 is a long problem, okay? So you really need to go through it in detail. It says hydrogen iodide, HI, molecule has equilibrium separation. So it gave you already R naught, the separation before this molecule. So from here, you can find the reduced mass between hydrogen and iodine. Iodine, you have its mass. They give you the mass for hydrogen. They give you the mass for iodine, also both of them. And they gave you the vibrational frequency, omega, okay, which is square root of K prime over M, okay? But who cares about that? We already have omega. So that's all we need for this. Calculate the moment of inertia, so for this molecule. So again, the moment of inertia is just the reduced mass times the square of that equilibrium separation, okay? Squared, that value has to be squared, okay? And we argued for that in class why that is, okay? And actually, I think this is just a physics 1 issue, how to find the moment of inertia for two systems that are basically in this situation. Okay, calculate the wavelength of the photon emitted in each of the following vibrational vibrations. Okay, now you have two energies, so you really have to be careful in this problem and look at the sum of the two energies in this case, because you have vibrations and you have rotations. And that is the sum of the two values for 42.3 and 42.7, the two values, where square root of K prime over MR, in this case is omega, it's given to you. So you really don't need to worry about that value of K prime. Otherwise, if you're really interested, you can find what K prime is, since you know what the reduced mass is. And then you have the value of EL. So you combine these two, and then you're going to go through all of these transitions in here from n equals to 1, L equals to 1, to n equals to 0 and L equals to 0, and then also n equals to 1, L equals to 2, and so on and so forth. Okay, it's long, but I hope that you guys can manage it. Okay, relying on those two formulas. Yes.
Yep.
Okay. 44. 44 is really, it's not too different than one of the problems from the previous chapter where you had that distribution, probability distribution. Basically, this is distribution that you find and take its derivative and find its value. This is similar to that, except that you're modeling, in this case, sodium chloride as being given by that potential. In order to find the equilibrium position, you take the derivative of the potential, you equate it to 0, and that should give you the position of the equilibrium and answer all of the related questions after that. Okay. Problem 45, I think that's also one of the problems. Metallic lithium has a BCC structure. Each unit is a cube, so they give you 8, the atomic distance for a BCC lattice, which is the number of atoms per unit volume. Okay, we're looking at a body-centered cubic. So you have 1/8 from the other side. 8 times 1/8, that's 1, plus 1 inside, that's 2. So 2 per unit volume. And then how many electrons per unit cell? So there are 2 per unit cell, okay? And then you can find the number per unit volume. So you have the density of the electron carriers in this case, okay? Use the result from part A to calculate 0 Fermi energy level EF naught. So once you find what N over V is, again, you have 2 per cell, okay? And then you have the cell volume itself, which is just that number cubed, 0.35 times 0.35 times 0.35 cubed. But don't forget, it's in nanometers, 10 to the negative 27 at the end, okay? Because 10 to the negative 9 times 3, so it's 10 to the negative 27. And you take that number of 2 divided by that gives you N over V. So it's going to be a huge number of 10 to the power 28. And that's typical for a metal. And this is lithium, so it's a metal. And lithium has a valence of 1. So it's good. So you don't really need to worry about how many charge carriers. So all you have to do is multiply it by 1. So at the end of the day, plug that into the expression for the Fermi energy level, and you should be in good shape. And the Fermi energy level is given by equation that is not listed toward the end, but we calculate, we have it, we discussed it in extensively, and I know that you did it in the part of that post test. So the energy Fermi level, what is the expression? The whole expression. I mean, it's the whole thing at the end is yes, it's the equation 4220. 4220. So yeah, it's an ugly expression. It involves all of that 3 to the power 2/3 and pi to the power 4/3 and each bar to the power squared. And then the main thing is n to the power 2/3. And everybody else is just n is the mass of the electron in this case. So everything else is just a constant basically. So in this case, what you did was calculate n over v, which is little n, the charge carrier density in that conductor. And for that case, in this case, it's a lithium for that metal. And then you plug it into that expression 4220, and then you're in good shape. Okay. Did I give you 44.5? Oh, you know what, guys? I gave you the wrong thing in here, okay? I'm glad that we caught this one. I'm going to send a message to everybody, the ones who are not here. I was supposed to include 45 here, not with chapter 43, but it's good. We have it in here too. So 45 is included, okay? Did I not include it in the review or not? I may not have done that.
In the review, number 45 is not on chapter 42. I don't see it on the list there.
Yeah, it should have been. I'm sorry, it should have been, okay? It should have been. Because I just realized in my notes, I don't see it where it's supposed to be, and it is supposed to be. So 45 is important in here too, okay, from chapter 42, okay? And then 47. 47 is data, basically. Again, you're supposed to go through the data and interpret it. 49, 49 has that diode thing, okay? And the main thing is for the diode is the current is given by IS times the exponential of the voltage divided by KBT minus 1, okay? The minus is outside of the exponential, okay? So that is the value of the current. And you should be able to answer these questions. The first part in here, any predicted current less than 1 micrometer can be considered a zero current. Determine the minimum voltage V out for this one. So we're going to assume that it has reached the minimum, which is 1 microamp in this case, microamp, yes. Okay. And what is the voltage? You just use that expression to find what the voltage is. Okay, they gave you IS. IS is equal to 5 times 10 to the negative 13 amps. And you assume that the current I is equal to 10 to the negative 6 amp. And from here, you find what the voltage is. Remember, the voltage is in the exponential. So you have to take the natural log of the ratio of I over IS and add to it 1, because you have to move the 1 to the other side. And once you take the natural log, you're going to find EV over KBT. And they tell you T is 300 Kelvin and you have KB, so you should be, and E is the charge of the electron, so you should be able to find what the voltage is. Usually small voltage, that's what the voltage V out is, okay? And then the current increases dramatically for diode voltages that exceed that value. At a given diode voltage V out, the diode has an effective resistance as RD equal to V out over I. So this is as if it's an ohmic behavior, but it's not, you know, it's non-ohmic device. So we can find an effective resistance in there using this expression. Use equation 42.22, which is that exponential, I think. to estimate the voltage V out equal to V max. So, okay. You're going to equate the two sides now, basically. You're going to have a transcendental equation, an equation that is not easier to solve, except numerically, okay? So if you're good with Python or C++ or have any numerical calculator, you should be able to find the solution quickly. If not, then basically use the old method, which is graphing, and find where it intersects, where the two intersect, and that is what the solution is, okay? So there should not be an excuse not to do this one. Even if you're not comfortable with any programming language, you should be able to pull the data and put it on an Excel spreadsheet and plot the two and find the numerical solution where they intersect, okay? I think, I'm not 100% sure, even Excel has that intersect function between two graphs. I'm going to quickly Google it. Excel intersection of two lines. Oh, there is a. Okay. If you're not sure, Google it, and there is one. I'm looking at it in here. It's listed all over the place. Okay, honestly, I cannot really tell you. Does anybody know that there is some sort of a, okay, so that the lines, so they give you the two lines. Yeah, there is something called intercept. The Y value is 1, X value is 1, and the intercept X value is 2. I'm not sure, okay? Anybody who knows this? If not, you have to use trial and error. Excel. I'm going to open blank cost book, whatever they call it. And I'm going to come in here and say equal to enter. Yeah, there is an intercept. Okay, there is an intercept. I just entered. Okay, let me share with you the screen. Intercept. Oops. And these are the arguments. Okay. Non-YS and non-XS. I guess. Okay. I guess I need to experiment this thing in here. Honestly, I don't know. Okay. I don't know this. Okay. Anybody familiar with this one?
Nope, no idea.
Okay. Okay. Basically, you graph the two data and find them. Find where they intercept. Okay. If you're careful enough with the scaling of your graph, you can do it manually. You can print it and find the value using a ruler, basically, where they intercept. Okay. If you scaled it correctly, and if you're careful with it, so this is, remember, all is acceptable as long as you tell me exactly how you did it. Okay. So if you take the graph the data on one side, graph the function on one side, graph the function on the other side. This is how we used to do it before computers. Okay. And then take a ruler and find the point, find its X coordinate. Of course, the Y coordinate, they will match. And that is the value that you want to plug in for the value of the voltage in this case. Okay. Now, if you're comfortable with any of the programming languages, please tell me exactly what you used. And I would be more than happy to. I mean, I prefer as one of the two languages now. I'm still learning Python. I'm not really a Python guy, but I will understand it since I have compilers all over the place now, and I have the interpreters. They don't call them compilers for Python or C++ if you want to. Okay. Some of you might even do Java. I don't mind that too. Okay. So if you have any other method, please let me know. Okay. If you're using the graphical method, that is acceptable 100%. There is no shame in it. As a matter of fact, that's how I learned it myself, and a lot of people did it in the old days. Okay. Don't save. So especially with these problems. I remember when we were doing electronics, we used to do a lot of these things graphically because there is no other way. Okay. And so the rest of the questions, I suppose they're easy, especially in terms of the last part. Just usually you have to have that big resistor in there to kill any high currents. And you're going to have a value for the maximum voltage you're going to get in that situation. Okay. So this is the that problem. Let me continue with these things in here. And we need to expedite these things. 47, 49, 51, and 52. 51, you have a carbon dioxide molecule shown in the figure. Okay. I gave this problem when I was doing actually physics 1 class in the past, basically 250, where they find the different modes of vibrations for the for the molecule. Okay. Assuming that the molecule in this case has only linear motions. So in this case, you have the oxygen in this, the carbon in the center and the two oxygen atoms. So it could oscillate in such a way, the one in the middle is sitting still. The center of mass has basically to stay still. If the center of mass translates, you will have omega equal to 0. And that is actually one mode. Okay, omega equal to 0 is one solution. There are two other modes where the two oxygen atoms will move one way, both together, and the carbon will move in the opposite direction so that the center of mass stays in the same place. And there is another scenario where the two oxygen atoms move opposite to one another, and the carbon stays still, so that the center of mass doesn't change. So those are the three modes, omega equals to 0, and then there are two omegas, okay? So you should be able to find them. Once you do that, you're going to find the different values of omega. You're going to find different values of omega, different excitation levels, basically for the carbon dioxide in this case. You're given K prime, the spring constant between the oxygen and the carbon, and you're going to find the different frequencies that are associated with these oscillations. Obviously, the omega equal to 0 is translation, so that's not going to be something that you're going to see. Okay, it's not going to be something observed. So the only two values that you're going to find are the only two excited states that you're going to, the only two basically possible modes of oscillations that you're going to find. Okay, so if you have difficulty with this one, please let me know. Again, the calculation sometimes can be long. And if you did any kind of algebra, linear algebra, it should really be easier. But if you didn't do any linear algebra, it should not really be too hard either, because you can solve system of 3 equations with 3 unknowns in this case. This is something that you might learn down the road on something called the Eigen States and the eigenvalues. So in this case, the Eigen States are the modes of oscillations, and the eigenvalues are those values of frequencies in there. Okay. Remember, you're supposed to be preparing yourself for a higher level of education. So this is more of an introduction to those courses that are coming down the road. Okay. Anybody did any kind of linear algebra and familiar with the eigenstates and eigenvalues, with matrices and things like that?
I'm in it right now. That counts.
That counts.
Okay, very good. So you're on top of these things. And then the last one is a colorless, odorless. This is the last one? Yes, it is. Colorless odors in a tank needs to be identified. The gas is nitrogen, nitrogen or carbon monoxide or nitrogen oxide. White light is passed through it and a sample to obtain the spectrum among the others following frequency. So they give you lambda. So this have been absorbed. Okay, these frequencies have been absorbed because they are not there. They are not part of the spectrum. So you're looking at an absorption spectrum now. Okay. This represents from the lowest energy level state. What photon energies correspond to this wavelengths? So you're going to find E basically, which is HC over lambda. Specify your answers to 5-digit figures. Now they are picky about the precision. So you're not going to use 3 times 10 to the power 8. You're going to use 2.9979 10 to the power 8. And H given in electron volt, not in joules per second, but electron volt second. Which one of the observed energies corresponds to transition from L equals to 0 state to the gas? Okay. Hint, again, equation 42.9 along with the transition rules, guys. So you have several possibilities in this case, because then again, the reduced masses are given for this atoms, the interatomic gases are given, and you're going to go through basically forensics, trying to identify which one really is the one that is corresponding to each and every one of these frequencies. It's long, especially since you don't know, but at the end, you're going to tell me which one it is. They gave you the masses, they gave you the interatomic masses, it's in the picture on the next page. And you should be able to find I, okay? And you're not only concerned with I, you're not concerned only with the rotation, but also you have the omegas, okay? Because you're also worried about the vibrations. The good thing about this molecules, they are all diatomic, so you're not going to worry about those modes of oscillation from the previous problem, because there is only one, okay? The two are going in and out of one another, okay? So you're going to do the calculations in here. I hope that, I mean, it's long and it's probably, you have to be careful, especially with this high precision, to find which one is which, okay? We still have about 15 minutes to go through 2 more chapters, albeit there's a little bit less, so. (43) problem 44. 44, it says the nucleus of beryllium 4 undergoes a beta minus decay. The atomic mass of beryllium 4 is 10.01353 atomic mass, atomic unit masses. How much energy in mega electron volt is released in this decay? Okay, so we're given the mass of the beryllium, okay, and it's going to go, when it goes to a beta minus decay, that means one neutron has converted into a proton. That means the element is no longer beryllium, but it's a boron, actually. So it's moved on the periodic table. Okay, it's beryllium. Now it's this one, boron. So it basically has moved with from Z equal to 4 to Z equal to 5 now. Okay, so that's what the element is. How much energy in MeV is released? So what you got to do in this case is go back to that table for the masses of the lighter elements on this chapter and find the difference in masses between the beryllium and the boron and the electron that has been emitted. Okay. I'm just trying to find the table. Let me find the table first. 43 point something. 43.2 on page 1445. Okay, it gives you the boron 5, and it gives you it's 10.012937, and you need that much precision. And it gives you the beryllium in this case, which is an isotope that is not listed in there. Beryllium is not listed on the table, but they gave you the value in the book, in the problem, I'm sorry. So they gave you the isotope 10 of beryllium, which is 10.013535. So you need that number, and you need to subtract from it the mass of the electron that is emitted and the mass of the boron that is also produced, part of that decay. And you're going to find the difference in U, and then you're going to multiply it by 931.5 MeV, and then you're going to find exactly how much energy is released in this case, okay? If you assume that all of the energy released in the electron has been gone to the beta electron, a very accurate description, what is the speed of the emitted photon? To be on the safe side, use the relativistic expression. So that energy is K, which is MC the mass of the mc squared, which is the mass of the electron, times gamma minus 1. Compute gamma and find what the value of gamma is. If gamma is big enough, then hey, you're justified. If gamma is not, it's basically does not justify beta being very large, then in this case, hey, okay, you're in good shape. Okay, gamma is 1, then in this case you really could just have used 1/2 of mv squared, where m is the mass of the electron and v is the velocity in that case. If not, this expression should tell you exactly what the value of beta is. Okay. So this is this problem. And again, this is a beta minus decay. There is another possibility, and that is actually an electron capture, but they didn't tell you that there is an electron capture in this problem. So you're good. Problem 46. Calculate the minimum energy. Again, don't forget that that expression is critical. The sum of the masses before minus the sum of the masses after must be positive for a decay to happen to begin with, okay? And that gives you that energy. When in doubt, always use the relativistic expression, okay? That you're going to be on the safe side because it's more accurate in that case. Okay. Calculate the minimum energy required to move one proton from nucleus of carbon 12, I'm sorry. This is called the proton removal energy. Hence, find the energy difference between carbon 12, there is no such a thing, carbon 16. Nucleus and the mass of the proton plus the mass of the nucleus formed when the proton is removed. So we have carbon 12 and we want to remove a proton from it. For remove proton from it, we have a problem. Two things will happen. First of all, Z will be reduced by 1, and also A is going to be reduced by 1. Okay, so in this case, which element on the periodic table that has less than the oxygen is actually nitrogen. Nitrogen has 7. So boron, what I'm still thinking in terms of oxygen, okay, which is the next problem. Actually, these two problems are related, so we could very well be doing both problems in the same time. Okay, except the other one is actually 47 is actually a removal of a neutron, whereas this one is a removal of proton. So both problems are similar. So one of them, you have oxygen, removing from it a neutron will keep it as nitrogen, but it's an isotope now. But a carbon, removing from it a proton, will convert it actually into a boron, okay, in the periodic table. Again, I'm looking at these two things in here, okay? So again, you're going to compute the masses at the end, before, and the masses at the end, and you find how much energy is required. And again, to compare it to how much for the binding energy, you have to add all of the different components of that nucleus, the mass of the neutron, the mass of the protons, and that should give you a value for it, and you divide it by the number itself. You're going to find the mass per nucleon. You're going to find the ratio of that. How much really does it take to remove one proton? How much does it really take to remove one neutron? That's what these two problems are. Okay, I think these are easy problems. Unless you guys have difficulty with them, please let me know again. Okay, so we did 47 and 46. 45, since I mentioned it to you guys, this is not the 45 I meant. Sorry about that. So this 45 is not the one I meant. The only 45 I meant for this review is the one from chapter 42, not from chapter 43, okay? It has to do with the converting joules into masses and comparing fuel and things like that, that I am not really that, it's not gonna help us with this class. You guys got the point in here for 45, this confusion that I have already? Okay, sorry about that. That's my mistake. Like some of you say, my bad, okay? Although it's not proper English, okay? Because you need a noun, you don't need an adjective. Anyway, 50. 50 says thorium, 230, decays to radium 226 by alpha emission. The mass of the neutral atoms are 230 for thorium and 226 for radium with those decimal points. If the parent thorium nucleus is at rest, what is the kinetic energy of the emitted alpha particle? Alpha particle is too tiny, so you find the difference between the two energies. And that's going to be the energy basically of the alpha particle, because there is no, I mean, it tells you in here, be sure to account for the recoil motion of the daughter nucleus, which is in this case radium. Don't worry about that. Even if you include it, it's going to be a very, very tiny value. For the most part, that's the energy of the alpha particle. Okay, that's the point of this exercise. But if you want to calculate, go ahead and calculate the ratio of the two energies. You will find that it's a huge, I think like more than 90%, 99% or something goes to the alpha particle, and the rest, which is less than that, is just for the daughter particle in this case. Okay, the starting one, thorium, was at rest, so we are not worried about that. Okay, 51. Okay, I'm going to skip through these things. I assume that you guys can do the ones with the chart. And the rest of them, they're all calculating the difference in energy, because we have about 2 minutes left, and we have to go through chapter 44 to just give you a flavor also of what's happening in that chapter, because I don't want to leave that completely undone. So 38 from that chapter. Where is 38? Let's see. 38. So you have a proton and antiproton collide in a head-on collision to produce a gamma rays. Two gamma rays. Conservation of momentum requires two of them. Calculate the energy incident of the proton. They gave you the gamma ray energy, okay? And you know what the rest energy of the proton. You use a relativistic expression for it, which is just the sum of the two values, the kinetic energy plus the potential plus the rest energy in this case. You should be able to find the total energy. Who cares about that? So you calculate the kinetic energy of, just subtract from it the rest energy of the proton. But you have two of them. You have a proton, antiproton, and you have two gamma rays. Then the two cancels from both, because the two gamma rays are the same, and the proton and antiproton have the same energies, because they tell you they're in head-on collision. They have the same energies, and they have the same mass, so the charge doesn't, nobody cares about it when it comes to relativistic values in that. So the two cancel, so at the end, you equate the total energy of the incoming proton to that of the gamma, one of the gamma ones, and cancel and move the rest energy to the other side. You'll find what the kinetic energy is going to be, okay? So that's that one. Problem 41. Problem 41 and 42 actually, or 41 at least. It tells you, go through this expressions, and they give you 4 or 5 of them, and tell me the particle that we're missing. We have a proton, give us a proton and a lambda not particle. So this particle in here must be charged particle. First of all, in terms of the baryon numbers, they're conserved because a lambda particle is a baryon, proton is a baryon. So this is not a baryon, okay, for sure. And then also in terms of for this case, the lepton numbers, they're 0 in the beginning and 0 at the end. So we really don't have any lepton properties. So this must be a meson of some sort, okay? The reason why we need a meson in this case, because it's a charged particle, because I have 2 charges in the beginning and I have only 1 charge at the end, because the lambda particle is lambda naught is not charged. So this has a charge value. And so you go through the chart in there, and then also the strangeness. It has to have a strange value of 1, because this one lambda naught is actually -1. So in this case, you have all of the properties. Again, you go back in the table and look at it and identify that particle that is missing from this expression. Same thing with the next reaction. So cation negative plus a neutron is equal to a lambda naught. Well, this particle must be charged to begin with. And then you go through the list of all of the L's. In this case, they're 0. And the baryon number is the same in this case too, because kaons are not, they're mesons. So in this case, you have N, which has a baryon number of 1, and lambda naught has 1. So in this case, it's conserved. So again, you go through all of the conservation values, and you're going to be in that shape. I know I'm exceeding time, so hopefully, if you guys don't want to stick around, that's fine. I'm going to finish it and then post the recording, so you can come back later into it. So we're 1 minute over time. Sorry about that. And then the next problem, so it's the next for the next equation, so it should be the same thing. The next problem, it gives you an eta naught meson at rest decays into a pi meson. What are the allowed values for pi naught, pi plus, and pi minus as they decay? So we start with a charged particle that is 0, and the only outcomes are any of those combinations. So they want to know which combinations are allowed. So in this case, the only combinations is either you have 3 pi naught particles. So you have a pi naught, pi naught, pi naught, or all of them, a pi naught and a pi plus and a pi minus, so that the charge is 0, because the charge needs to be conserved. So that's basically what dictates that decay, which one of these decays are allowed. Find the total kinetic energy of the pi mesons. So in this case, as it decays, it could decay to a pi naught. So you'll have 3 times pi naughts and subtract it from an eta naught. Then you're going to find the energy. Or you add up all of those values of the energies for a pi naught and a pi plus and a pi minus. Those are the pi n positive, pi n plus, pi n minus, and the pi n naught. And you add them all, and you will find what the other particle is, what the energy is. So this should be straightforward from that. And then we said 48 and 49. 48 and 49, you have the Xi. I call it Xi because that's how they call it in Greece. And I don't know, probably it should be Xi or something. I don't know how they. A Xi minus particle at rest decays into a lambda naught and pi n negative. Find the total kinetic energy of the product, what fraction of the energy carried by each particle, use a relativistic expression. This is kind of a long calculation, but you have conservation of momentum and conservation of also of energy, but and you have the values for different masses, so you should be able to do the calculations, okay? And 44.9, 49, I'm sorry. A sigma minus particle moving in the plus x direction, and with kinetic energy 180 mega electron volt and a pi n minus and a neutron. It decays into a pi n minus and a neutron. The pi n minus moves in the plus y direction. What is the kinetic energy of the neutron? So basically, again, you go through relativistic calculations. Don't forget you have conservation of momentum in this case too. You should be able to find the vectors. You should be able to do these calculations are a little bit long, but they should be doable. Okay, it's not too different from problems we did before. Okay, and then 50 is just a table. Okay, 50 is just a table. If you have any kind of a specific question, please, related to any one of these problems, send it to me. Okay. If I think it's something minor that can be discussed together, we can discuss it. Basically, I can reply to you, oh no, you're supposed to forget an H bar in here, or you're supposed to include 2 particles, or you're missing 1, or something like that. If it's involved, what I can do for you is, first of all, share it with the entire class. One way, either record it or send it through print, okay? So please go through all of them. Make sure don't leave any one of these problems basically unchecked. Check them all. Make sure that you have all of them done. And if you are in doubt about anything, please communicate with me. I am available for you. Tomorrow morning, I know I have classes tomorrow between 11 a.m. until like 3 p.m. I'm not available. And if I don't answer you during that time, is because I'm, like I said, I'm teaching. If not, just send me messages and hopefully we can do that. Available all day today and then tomorrow also, unless those times which I'm not available because actually I'm teaching in class at that time. Well, sorry for taking longer. Thank you for sticking around. For those who left, this was not too long, at least the extension was not too long. So thank you. I will see you guys on Thursday, unless you... Oh, I forgot to mention, please do the survey, okay? Only 5 of you did it so far, and I'm going to follow up with a message. Thank you, guys.
Professor, I actually have a quick question.
Yes, go ahead.
It's about my chapter 44 quiz that I took yesterday. I was wondering
Okay, hold on. If we're going to talk quizzes, Is it something related to grades or a work or something or not?
Yes.
Okay, then in this case, we should really meet. First of all, I have to stop the recording.
Sorry.